Welcome everyone to my presentation on reconciling spatial and temporal abstractions for Go representation. So we want to solve long horizon tasks, which typically involve multiple goals that need to be achieved before the problem is solved. This is typically difficult for standard reinforcement learning techniques without some kind of reward shading or pre-engineering. If you look at this ant robot, you can see that it's already pretty difficult to learn how to move it, let alone place it in a maze where it has to maneuver around some obstacles and reach an exit. This is actually why we turn to hierarchical reinforcement learning, which proposes to decompose these long problems by setting up some simple learning goals. The issue is that without an appropriate goal representation, HRL algorithms can be pretty inefficient. Our work is based on GARA, which is an HRL algorithm where a high-level agent proposes an abstract goal to a low-level agent, which in turn takes actions into the environment to best reach this goal. GARA is defined by an abstract representation for goals, which is learned through refinement. This abstraction is called reachability-aware goal abstraction, and it is essentially a set-based goal space where every goal is a set of states. This corresponds to a spatial abstraction. Looking at this maze example, G0 and G1 are both abstract goals that are sets of states. The high-level agent will target G1, and the low-level agent will slowly reach it. One can conduct reachability analysis on the set of states that are reached and split G0 into two sets of states where G0 prime contains states that all go to G1, whereas G0 second contains states that all do not go to G1. And this is how you group states that have similar environment dynamics. We solved two problems in this paper, the first of which is conducting or establishing theoretical guarantees on the reachability-aware abstraction, and then second, scaling this abstraction to adhere to complex environments. And so our contributions are twofold. First is we conduct a theoretical study on the abstraction, and then second, we introduce a hierarchical reinforcement learning algorithm STAR that leverages both the spatial abstraction and the temporal abstraction mechanism to scale to complex environments. First are the theoretical guarantees, where we prove that the policy learned under abstraction has a bounded suboptimality, and then the reachability-aware goal abstraction can be obtained in a finite number of refinements. Second is the scalability issue, and the core assumption of the reachability-aware abstraction is that it requires successful policies. And so transitioning from G0 to G1 is not always guaranteed to be feasible initially, especially in complex environments. And so the refinement process will be blocked in this case. One way to solve the problem is to introduce temporal abstraction in addition to the spatial abstraction, which essentially revolves around proposing subgoals, which are points in the environment that the low-level agent can follow to reach the set of states that is desired. We implement this process into the STAR algorithm that contains three agents now, a commander choosing the best set of states to visit, a tutor choosing these subgoals as points in the state space, and then the controller following these subgoals towards the set of states. And so to evaluate STAR, we compare with baselines that either use spatial abstraction only, temporal abstraction only, or reachability analysis conducted on a state-by-state basis in a track. And so in ant maze, we can see that STAR in orange is on par with the state of art, but when we move into ant fall, the ant has to push a block to create a bridge-like structure to the other side, and this is where STAR is more data efficient. And consistently, in ant maze scam, where the ant has to look at a camera to unlock the obstacle, we can see that the reachability-aware abstraction outperforms its state-by-state counterpart. And so to conclude, STAR leverages both spatial and temporal abstractions for data efficient learning, and the reachability-aware goal abstraction can scale to more complex environments. Thank you.